Okay. Hi, everyone. My name is Jethro. I'm a second-year computer engineering student here at UNSW. My main passion is in hardware, which is why it's kind of ironic that I'm here to talk to you guys today about some really pretty math stuff that I've come across. Yeah, this past term, I've been doing Comp 3821, extended algorithm design and analysis, and yeah, just found some really pretty stuff in maths that I'm gonna be talking about. So, little kind of overview. We're going to start by looking at what graph coloring actually is, as well as a brief introduction to Markov chains. I'm then going to present a technique used in probability theory called coupling. Then how that eventually got generalized by some really smart mathematicians into path coupling, which is what this talk's all about. And then kind of just tying all together, talking about what I got out of it, and yeah, what it means overall. So first off, thank you, Linsock, for organizing this. Very epic event. Thoroughly enjoy the opportunity. Also, 3821 course staff. It was pretty good, of course. And then yeah, my group members, they did cool stuff, and my project supervisor, because a lot of my group members' work is in here. So starting off, for those of you who are not well versed in computer science. Graph coloring is a pretty famous problem. Basically, you define a graph, right, which is a set of dots and lines between them. And the question is, is it possible, given a set of like a certain number of colors, to assign a color to each vertex such that each adjacent vertex is a different color, right? So here we can see one graph coloring, right, because none of the points that are connected by a line share the same color. And here. We can see another graph coloring, except that this graph coloring is actually the same graph coloring. They're in isometry because the colors, although the colors are different, you can basically just set the green to blue, the blue to red, and the red to green, and you have the same assortment of colors, right? So it's the same coloring, even if the colors are different, because you can just assign the colors arbitrarily. So in terms of like when you're actually dealing with it, mathematically, it's not useful to like talk about it in terms of, yeah, we're going to use like red, blue, green, yellow, and gray for this one, right? Usually you just assign a number to each one, and then you also have a vector representing the coloring, where the index is the vertex and the color is the number at that vertex. Now, the reason it's quite a famous problem is because it is NP complete, meaning it is at least as hard as every problem in NP, and also it is, but that's the NP hard part. But it is also in NP, right? So to talk a bit about what that means, if you consider a problem like sorting a list, that's something in P, meaning you can do it in polynomial time. In other words, fast. K coloring, very not fast. So enter randomness. So if you don't really care about doing it deterministically, i.e., you want it to be fast, but there might be some variance in how long it takes. Well, we can do something like the following. Just pick any coloring. Doesn't have to be a valid one. You then pick a vertex uniformly at random and pick a color uniformly at random. And then you look in the neighborhood of that vertex. You check, is that color, neighborhood meaning like any vertices connected by an edge to that vertex, is that color in the neighborhood of that vertex? If it is, then skip and try again. If it isn't, then update it. Now, this algorithm has a name. It's called the Metropolis chain, and it is a Markov chain. Now, Markov chain is basically just any kind of system where the next state depends. Like what the probability of the next state depends on the current state and nothing else. So this is like just one application of them. Turns out you can use them to solve a huge range of problems, which typically these algorithms are just called like Markov chain Monte Carlo methods, is like the general umbrella term for all of them. Another thing that's worth mentioning is that we've kind of, you may notice, by these rules we've defined, we said you can pick any coloring, it doesn't have to be valid. If it is a valid coloring, this set of rules will never generate an invalid one. So in other words, you can transition from an invalid coloring to a valid coloring, but never the other way around. And this will come into play later. So why do we care about this? The short answer is it's fun. But the real answer is it does actually have some applications. So where before the problem was just finding if a K coloring exists, now we can do something a little more interesting, which is find every K coloring of a graph, right? Because as I said earlier, once you enter into a valid coloring, you can only transition to other valid colorings. So you can, in theory, just keep running the chain, and you will eventually, under certain conditions, sample the entire, like every valid coloring of that graph. And an application of this is in the Ising model, which is in physics. Say you've invented a new material, and you want to know about its magnetic properties. Specifically, you want to know at what below what temperature it is, like above what temperature it ceases to become magnetic. So there's actually a Markov chain that describes this called the Glauber dynamics. And it works by sampling a vertex at random, considering, worth mentioning as well, the colors in this are spin states. Your graph is a 2D lattice. You sample a vertex at random. You look at the energies in that neighborhood. And you depending on the energy in that neighborhood, that gives you your probability of flipping the spin. And what you find is that if the critical temperature, if the temperature parameter you give it is above the critical temperature, then it will converge to the state space of to a state space of a lot of different colorings. In other words, you can just keep running it, and it'll keep sampling from like a massive wide range of configurations. Whereas if you're below the critical temperature, it will converge to a single coloring and basically never move from there. Cool. Now we've got the boring part out of the way. Let's talk maths. So, as I said, under some conditions, a Markov chain can converge to a stationary distribution. In other words, instead of the next state only depending on the current state, you can basically just treat it like a normal probability distribution for all intents and purposes. And this can be represented by, we call this the stationary distribution. We denote with pi. P is the transition matrix of the Markov chain, which we'll look at that a little bit. And some of you may recognize this as basically saying that the stationary distribution is a row eigenvector of the transition matrix. Now, there's a lot of conditions that force this to happen. I won't go into too much of it, but the two kind of main ones is if you have a chain with a self-cycle where every state is reachable from every other state, then your chain is probably ergodic, meaning that the stationary distribution, meaning that it has a stationary distribution, basically. That is reachable. So, I think Krita was mentioned earlier. Krita, my goat. Thank you, Krita, for providing great code, and also thank you, Arch packages. I did not know it was that difficult to to do that. So let's look at an example Markov chain, right? This has got two states. The probabilities of going from state 1 to itself is 0.9, from state 0 to itself is 0.8, and then between them is 0.2 and 0.1. So you can represent that as the transition matrix, right? Where basically the 0, 0 element corresponds to the probability if you're in state 0 of going back to state 0. And this 0.2 corresponds to your in state 0 and you're going to state 1. And you can find that it does have a left eigenvector that is 1/3, 2/3 with an eigenvalue of 1, right? Which basically means that if you run this chain indefinitely, it will just converge to this distribution, right? Of telling you where this corresponds to the probability of finding an object in state 0 and the probability of finding an object in state 1. However, if we look at another example, in this case, probability of transitioning between them is 1 and to themselves is 0. Well, there are some row eigenvectors, but this one you may notice, no matter how many times you raise this to some power n, it's never going to reach this. It's never going to reach this vector. And the problem with this vector is that it has an eigenvalue of -1, meaning that basically each time you run it, it's going to flip to the other side. And this one is reachable. Obviously not this exact vector, to be a scalar multiple of it. And that corresponds to basically if we look back here. if you start in a configuration of, say, like, I don't know, 1, 0, right? So like 100% of your objects are in this one, then it's just going to keep oscillating back and forth. And so you're never going to hit a stationary distribution, because it's just going to keep, the stationary distribution is going to oscillate with a period of 2 steps, right? Cool. So now we're going to talk a little bit about mixing time. So first of all, the total variation distance is a measurement of basically the difference of 2 different probability distributions. It is basically, if you have 2 distributions, mu and tau, and you want to know the total variation distance between them, you basically just look at like the maximum over the probability space, the maximum difference between them of that event occurring. They have to be defined on the same probability space. That's another important thing. And the definition of the mixing time is basically saying that this notation here basically means the probability of finding between x, 0, and pi. Yeah, probability of an event given any starting configuration and the stationary distribution. That's what this means here. The dot means basically any starting configuration is less than some epsilon, which is arbitrary. However, it can't be more than 0.5. Otherwise, it is just completely irrelevant, doesn't mean anything. And typically, people just say a quarter is a good measurement for that. All right. Now, got all that out of the way. We can start talking about some of the actual cool methods that have existed in the field for quite a while. So, what is coupling? Well, coupling is a method that basically you condition 2 random variables on each other, such that you can say something about them. And oftentimes this corresponds to, like, you create an inequality between them, which lets you then prove something else. Strictly speaking, it's defined as this thing here, where these are once again distributions, and you're basically defining 2 new variables such that the probability that x is some state is equal to the probability that that distribution is that state, and same thing for this one, right? In other words, you're relating the marginal distribution of this one with respect to x is that, and same here. And we're going to look, this is all very abstract at the moment, but we're going to see how you can apply this to show some really interesting things. So an example is, say you want to do the random walk on a hypercube. So you can represent, say, just like a 3-dimensional cube, right? You can represent the vertices as coordinates, right? So say you have it start at 0, 0, 0, and the opposite corner is at 1, 1, 1. Then you basically have coordinates for like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? And so you can basically just represent a vertex of the hypercube as a binary string. And so we're going to do exactly that, right? Hence why this is here. This just means like every permutation of 0 and 1 up to that up to length n. And so what we're going to do is that we're going to just pick a vertex to start off, and we're going to pick a bit uniformly at random, and there's a 50% chance we're going to update it to 0, and 50% chance we're going to update it to 1. So that's our algorithm for how we're going to randomly walk the hypercube. And what we want to find is how long it's going to take before we have seen every single vertex. So we're going to make a coupling. So let's say now we have 2 chains, okay? And in both of them, we're going to pick the same vertex, right? So we condition them. We basically say they're conditional on the same random variable. So they're always going to pick the same bit, right? And they're always going to agree as well on what bit they're going to update it to. So the key thing to note here is that let's say you're doing it on a square, right? And you pick the coordinate 0, 1, and then your random variable says to update it to 1. Well, then both of your chains are now going to agree on that bit, right? And every step after that, they're still going to agree on that bit because they can only ever be updated to the same thing. So basically what we're looking for now is just the probability that given a time t, every single bit has been selected at least once. So we're going to let tau denote the number of steps before every bit has been selected at least once, and a sub I denote the event that the ith bit has not been selected among the first this arbitrary number of steps. Now, the thing here is, right, this looks like a really weird number. A lot of these proofs, the way you typically go about them is you just put a placeholder in here, do all the rest of the math, and then work out what you need to put in here such that it actually means something useful. And we'll see why this shows up in a bit. Because then we can say that the probability that sorry, brain. Okay, yeah. The probability that no, yeah. Yeah, so the probability that the number of steps required for every bit to have been selected at least once is greater than this thing is equal to the union of all of these things, right? Which makes sense because you're basically saying that after all these things have occurred, you have selected every bit, right? And this just comes from classic like inclusion exclusion. You can bound it by this sum. And that's quite a common thing you see in these proofs is just like big upper bounds on things because it's too hard to work with these other representations. So because every time you pick a bit, you then no longer care about that bit anymore. You're basically reducing every time you pick a bit, your chance of picking a useful bit in the future decreases by, well, 1 on n, right? So from that, you end up with this sum from the previous equation, which you can bound by this, which results in this. And then what you can basically do, because what we care about, right, for the mixing time is when this d of t here, this means the distance, the total variation distance between the current distribution of the chain and the stationary distribution. And we care about this being less than a quarter or less than epsilon, right? So you basically just sub in d of t equals epsilon, and you arrive at this nice expression here. In other words, we find that the mixing time is polynomial, and specifically it's O of n log n. As for graph coloring, if we remember our rules from before, you pick a vertex at random, pick a color at random, try and update it if it's allowed. So our coupling rule is going to be both chains are going to pick the same vertex and color, and we're going to treat the distance between them as the Hamming distance. In other words, the number of disagreeing vertices. So once again, big thanks to Critter. Here's an example of like two initial colorings, right, for the graphs. So you can pick any two colorings, right? And there's basically a few cases we need to consider. We can consider a good move, right? So a good move, this is a case where it's selected this top right vertex here, and it's updated them both to be green. Now for this one, nothing changed because it was already green. And for this one, it was a valid change, so it did it. And now the distance between these two has decreased by 1. There are also bad moves. A bad move is, for example, in this one, it selects this red vertex and tries to update it to green. Now, these are already the same, right? But if you update it to green in this chain, it's invalid, so it'll just remain red. Whereas this one, it is valid, so it'll remain green. This means that now you basically increase the distance between them by 1. Finally, there are also neutral moves. We don't really care about them. We'll see why. But yeah, you can, in this case, it's picked two vertices that were already different, which, no, not already different. They were already they were already different. Yeah, and then tried to update them. Both of them failed, right? Because this is invalid, and therefore the distance remains the same. So now we can consider basically all those cases, and basically compute the expected value of the next state given the current state on average, right? Which this part comes from the current state. This part comes from the good moves, right? You're basically saying there's a k minus 2 delta on kn chance of the good move happening. Where also something to say. K is the number of colors. Delta is the maximum degree of your vertices. This comes from the fact that there are k minus 2 delta good colors, basically. Not quite. There's a whole. It's very involved. I could go over it, but I think we'll be stuck for time. Yeah, and basically just evaluates to this nice expression here. And then this is where it gets really, really ugly, because now you have to recursively apply this inequality across every single pair of states, right? Very, very involved. You have to basically see some magic exponential thing that you can bound it by this. And then you basically have that so long as k is greater than 4 delta plus 1, then this should rapidly mix. Now, this was a very ugly process, right? And for a long, long time, this was basically what people in the field were stuck with. Yeah, so especially the bit where we had to recursively apply all the couplings, very, very painful. Lots of inequalities with exponentials. There was also a brief period when the main way of analyzing these was with spectral gap analysis, which is basically where you're doing all manner of linear algebra on the transition matrix and trying to show properties through that. This was even more ugly. I have read there are like 30-page proofs that exist for this. And then, anyway, so there was a bit of a dark age in the field. No one really, okay, I say dark age. It was a very new field, so no one really knew what they were doing. But then, in 1997, Baldi and Dyer released a paper describing path coupling. One sec, guys. Okay. So, just a bit more setup before we can get to what path coupling actually is. Start off by defining a pre-metric, which is just a weighted connected undirected graph, right? So you're somehow relating every vertex to every other vertex, right? And then saying, well, not every vertex to every other vertex, but it has to be connected. So there's one component. And then there's also an added requirement on this pre-metric that if there's an edge between two vertices, then that has to be the shortest path between them. You can't have any shorter paths that take a different set of edges, basically. And this lets us then we can then basically extend this shortest path metric, which we're going to call small delta, right? And what we can do with this, we will see in a second. So if we can couple any two states now in this graph, right, and consider the shortest path between them, which is always going to be some sequence of edges, right? And then we can compose them all as we did just now, right? We're basically just doing the same set of steps that we just did for the coupling argument, except we're generalizing it. So that instead of using that one specific coupling, we're saying how can we apply this to an entire class of couplings, specifically those where we're considering a distance metric, like a shortest path metric on that particular kind of pre-metric. And so then we get this wonderful expression where we're basically saying that the expected distance so if we've got our two chains, the expected distance between them after running it for one step, given the current state, is at least less than or equal to the expected value of this big sum, right? Which is basically the how we did before when we recursively applied it to every adjacent coupling, which this expression is the same thing as this right here, because you're saying that by our earlier metric definition, the distance between any two subsequent states in this in this chain must be smaller. And so overall, we arrive at this here, which is actually a very powerful expression, because what it lets us say is that basically the chain will mix in 1 on alpha log d time, where I'll get to what d is in a second. But the reason that comes up is because you're effectively saying that you're dividing the distance between them by this amount every time. And the diameter is the longest distance between any two states in the graph. Cool. So now we're going to look at how we can actually apply that to the graph coloring problem. Oh yeah, first off, let me just okay. This is a brief animation of what it shows is kind of it just shows two graphs approaching like running the same chain next to each other, and basically you get to see how long it takes for them to converge, right? So you see that's sort of pretty far apart, and then as the chain is run repeatedly, you eventually get to the point where they just sync up, and then from henceforth they're always going to agree. And so by using a path coupling argument, you're basically taking each step of that, bounding it by some amount, and then recursively applying that bound with that general form from earlier. Cool. So we're going to look at our exact same chain as before, except we're going to couple it slightly differently. The main difference is that now, if we pick, first of all, okay, the first thing we're going to say is that the two chains start in configurations that are exactly one vertex apart, right? So they agree on every color except one. Then, if one of the chains picks if the random variable selects a vertex that is in the neighborhood of that vertex that's the same, then if it also picks the color of the vertex that's different, then the other chain will pick the color of its vertex that's different. And the same thing in the other direction. So basically, yeah, if it tries to update the color and it's not possible for the second graph, then it will pick the first graph's color. And if it picks a color that's not possible for the second graph, then then it will pick the first graph's color as well. Yes. Cool. Otherwise, everything is the exact same. Now, you may be wondering why do you have to do it this way? Remember, a condition on our coupling is that they have to be on the exact same state space. If you were to say, for example, if C equals Cx of V, Y also picks Cx of V, and then if C equals Cy of V, then Y also picks Cx of V, you would have that Y would basically only sample one less state, so it wouldn't have the same state space. So in our first case, we have that we pick the vertex that's different, in which case the distance between them will decrease with this probability because there are k colors minus delta invalid colors, right, for each vertex adjacent, divided by kn. And then the second case is where we pick something in the neighborhood. This one's a little more complicated. There's a few cases to consider, but the only one we care about is that case earlier, this one here. Because if it picks the second chain's color, then this one will update to the second chain's color, and this one will update to the first chain's color. So they were the same before, but now they've actually changed, and so your distance increases. And that will happen with that probability there. And the other case is invariant. There's no distance change, so we're all good. We then apply our coupling the exact same way as earlier, and we find that the expected distance is less than or equal to this number, which, if we look at our earlier expression for, here, right, our delta of xy was just 1, right? We said that in the, like we specified that at the start of the problem. So our alpha is 1 on kn. And therefore, we can use that expression from earlier to say that the chain mixes in O of kn log n, which is very cool. We've basically just made, we've reduced the bound from before it was 4 delta plus 1. Now it's 2 delta plus 1. So slowly, getting the possible like classes of graphs that we can run this on to be like a bigger and bigger group of graphs. Yeah. So kind of takeaways and stuff, I guess. I just think this is a really pretty demonstration because they've taken something that was so ugly, so difficult to, you just have to kind of sit down and slog it out with all these disgusting inequalities, and generalize it to a point where you basically just show like a few small things and then the math kind of just does it for you. Especially looking compared to like the spectral analysis stuff, this is just so much nicer. And it's kind of awesome that you can just do that. You can take something so general and turn it into, you basically use math as a tool to generalize it even further. Other than that, once again, like why kind of do we care about it? There's been a whole lot of research into it recently. Particularly the bound has been reduced to as far as k greater than or equal to 11 on 6 delta. So that's as far as we've got. And there's a big conjecture in the field that it is rapidly mixing for k greater than or equal to d degree plus 1, which would be huge news because then you're almost at the point where it can deal with like most classes. Like you can find a smaller and smaller coloring, which is useful in a lot of cases where you care about having a smaller coloring. E.g. for timetabling is an example where you want to have things overlap basically your timetabling is more efficient the lower the colors you consider are. As for what my group actually did, we basically looked at two novel chains. The main kind of interesting one is one where instead of picking the color uniformly at random, you actually weight it based on the frequency that the colors show up already. So the more a color is already in your graph, the less likely it is to pick it. And we sort of conjectured, okay, this is going to do really badly on star graphs because you can, for example, you can two-color a star graph trivially. You just say middle point is one color, every other point is a different color, and it would always weight the outer colors worse, even though it needs to pick more of them, right? And surprisingly, we ran this several times. It was consistent. This is the mean time to first valid coloring on a star graph. This one here. Blue is our novel algorithm, and orange is Metropolis, and it performs like significantly better. So a big thing is going to be trying to work out why that is. So nothing's been formally proved. For somewhat obvious reasons, it's very, very, very difficult to do a path coupling argument for this kind of chain because you basically multiply the number of states you have to consider by k. But hopefully we'll get somewhere. Other takeaways, research is fun. I've had a great time doing this. It's been really cool just like diving into stuff without, it's a lot of freedom involved, especially compared to like the rest of university. I kind of wish it was more self-motivated in other classes. I feel like so much stuff is just prescribed and you don't really get to explore stuff yourself. That said, probably not going to do any more algorithms research. That's probably enough for me. A little too abstract. My heart's still with hardware. Yeah, cool. Thank you.
All right, so we have any questions?
Yes. So you said that the field is getting better and they're finding more and more efficient algorithms. At what rate are those filtering into the real world or implementations? Like, I mean,
Not really. Well, okay. So the applications of this are actually quite scarce. They're basically only useful in scientific computing. You will not see these in many like actual applications that you're going to use on the day-to-day. My Discord is on. I should turn that off. Damn it. Okay. So practically none at all is what I'm going to say. There is also a kind of more general application of this to if you want some like really strangely shaped distribution. This is very useful for doing that because you can, it's quite, randomness is a difficult problem for computers to do. You can basically describe this set of like, sort of like, I guess deterministic steps in such a way that you can make whatever sort of strange stationary distribution you want. Like I've seen examples where people wanted a like 6-modal distribution for something, and the way they got their computer to do that is to find a Markov chain that mixes to something that looks like that. But yeah, applications, there's basically just that physics thing I mentioned. And in terms of like finding approximation algorithms for like, if you only care about finding a coloring and not like several, there are better ways of doing it than this currently.
Yeah, so there are limited applications, but for those applications, like if it's, physics, let's say NASA's running Ruby, what are the odds that the Ruby version they're using is going to have the faster, the 11/6 version instead of the 4 version? Considering
that paper came out this year, I think very unlikely.
Ruby moves fast, but yeah, that's all from me. Anyone else?
Yeah, so I have a question. You mentioned something about timetabling and like the coloring.
Yes.
So like register allocation in compilers is basically a graph coloring problem.
Yes.
And I was just asking, maybe is there any like applications towards that?
Okay, so it's interesting you mentioned that specific case because my understanding is that give me a second to think. You can also reduce register allocation to satisfiability, which is another NP-complete problem, but is a lot easier for computers to do. In most cases, they can do it like very fast. So this is probably still not the best way of doing register allocation. You'd be better off using whatever 3-sat implementation you have. So yeah.
Yeah. Okay. All right.
Is it for everyone?
All right. It's good.
Yeah.